Hello, I hope that you are doing well in your school internship. So let's continue our sessions of mathematics where mostly we are doing this one to help you to revise your contents. So as you see here, today's session follows the previous one is where you discussed with the how to find the any fruit of the complex number in this complex instead of the complex numbers. Now, you know that with our teacher we discussed about this one, but it is going to help us to graph or to represent graphically this any fruit of those complex numbers. I hope that you revised well those techniques and strategies to find the any fruit of the complex numbers. If not, please go back to the last session and try to study how to find the any fruit of the complex number, because it is going to help you to graph and to represent those any fruit of the complex number in the plane. It means that you cannot graph them while you don't know how to find them. So that's why I emphasize you to go back and try. If you are already, we are going to study how to represent those any fruit of the complex number where you discussed about it last time. For example, with your teacher last time, you described that for a given z in set of complex number where you have a plus bi, you can find the any fruit of this one. For example, zn, where you described how to find these values, where you discovered that this zk is equal to the any fruit of r, you remember, it is what? It is the modulus of this z given z. Then also you do what? You apply there's a cosine concepts. So sine, you can have a cosine of that angle argument of this complex number, then plus 2k I over n, then you add I sine of the angle, then plus 2k pi over n. And then after this one, I hope that you are able to use this formula to find those any fruit of any complex number, where this k, this our k is here, it is varies from 0 to n minus 1. It means if you are asked to find the cubic root of z, where you have a plus bi, it means what you have to talk about. If you remember last time, you find the modulus of this z, and it is our r, where you know that is equivalent to a squared plus b squared square roots. Then after you find the argument of this angle, and you remember that if both are positive, you can use tan inverse or arctan of this angle of b over a. Then you find those ones. What is necessary to find those any fruit of the complex number? It is to know how to find the modulus, this r radius, and also the angle of that one. Now, by today's, for example, for this case of any fruit, this means that n is equal to 3. So it means when we follow this one, our k will rise from 0, 1, and 2. That's just to remind you how to deal with to find the any fruit of any complex number by using these formulas. I hope that you are aware of this, and this can help us to graph those any fruit in the eigenplane. For example, let's say for a given z, where we have a za plus bi, and you found the zk of the complex number. You have to think that n r, or let's use a simple cis of angle plus n k pi I, k, 2k pi over n. Then to represent graphically the zk or any fruit of the complex number for given n is any fruit of that complex number. To represent this graphically, we need to find the n fruits of that z, which is a plus bi. Then we can find, for example, zk. For example, let's say n. For example, n varies. N varies also from 1 up to n. That n. And also k. We have seen that is varies from 1, 0, 1, 2 up to n minus 1. Then what you do, it is to find this zk, the n fruit of that complex number. Then after finding them, you remember how to represent or to graph or to represent z. For example, you can have zk. Zk varies also, it is equal to a, let's use another variable a plus yi. It is the same. Then, and here we have n, depends to the value of n. And also, after this one, to represent this, we use this, what we call eigenplane. And you remember that this is our real part, and this is our imaginary part. After finding those any fruit of that complex number, you represent them. For example, here you have a 0, here you can have a 1, for example, here you have a 2, and you have 3, for example, then here you have a I, here you have a 2i, then here you have a negative I, negative 2i, and here you have a negative 1, negative 2, and so on and so forth. Then you can have more than this one. So for example, let's say for example you can have a z where you have a zk, for example, where any fruit of that one, for example, you can have a z0. Let's suppose a z0 is equal to I, for example, then z1 is equal to 1 and z2, for example, should be negative 1 and z3, for example, let's say the fourth root of that one, and that one is equal to negative I, for example. Let's suppose that this z0, z1, z2, and z3 are any fruit of any complex number. What is our task of today? It is to represent those any fruit of the complex number in the eigenplane. It is the same as to represent the an eigenplane those complex numbers. How to do so? For example, we have a z0. It is I. It means here you have it is a pure imaginary number. If it is a pure imaginary number, in this case, we can say that our point it is here. I, Z0, and we call it Z0 here. And we draw a line in this one. And also we have our Z1 is equal to 1. It is a pure real number. And it is this one, here we have a Z1. It means it is from 0 up to this one. And it also, this one, this interval, it is our modulus of that Z. Then you have a Z2, for example, it is negative 1. In this case, you have a negative 1 here. Here it is said that to be a Z2. And it is this one. And also we have, for example, Z3, it is negative I. It means it is our negative I. Here you have a Z3. That's just to illustrate those n fruit of the complex number in this Argand plane. What is necessary for representing n fruit of the complex numbers? It is only to know to find the modulus of that complex number. Then after you find the angle, the argument of that complex number, then another one it is to find those n fruits. Please, I invite you to be aware of finding the n fruit of those complex numbers. After getting those complex numbers, another task it is to represent them in this Argand plane. To represent them with all the ways we use to represent any complex number in the Argand plane. So I hope that you remember how to represent those complex numbers in the Argand plane. That's just a scenario how to deal with this, how to represent this one. The main hint to represent those ones it is to know how to find those any fruit of the complex numbers. So if there is any challenge from this one, we can have one example, then we proceed. The more task is for you to describe more cases where you can describe and draw or graph those complex numbers. So let's have one example from this one. So let's use this example to represent these four fruits of this z. Here it means that our z is equal to -4. And this complex number, it is pure real. Now, it is pure real number. In this case, this means that our z is equal to -4. Then, what is necessary to represent the roots of this number? The necessary to find this modulus, as I said, you find the modulus. And the modulus of this z is the same as an absolute value because it is just a real number. Then, or you can use this way and you find that it is equal to 4. Now, the angle of this argument of this z where it is equal to -4. In this case, you see that our b is equal to 0 and a is equal to -4. It means that this is in the second quadrant and also it is equal to pi. It means if you graph them to find this angle, we have -4 in the real part. -4, for example, you can say it is in here, -4. And if it is -4, we can say that this is 90 degrees, then after this one it is 180 degrees. That is how to find this angle. Now, after that, we need to find what does any fruit of the complex numbers. And you have seen that zk, here n will be equal to 4, because we have that one. And if n is equal to 4, it means that k is equal to 0, 1, 2, and 3, because it is n minus 1. Now, zk will be equal to the n, our n is 4, and our radius it is equal to 4. Then we multiply cosine of the angle, which is pi plus 2k pi over 4. Then plus I sine pi plus 2k pi over 4. This is our zk. Now, let's say for k equal to 0. If k is equal to 0, we have a z is 0. And if z is 0, we are going to have the 4th root of 4, and the cosine of, here it is 0, we remain with cosine pi over 4, then plus I sine k is equal to 0, we remain is pi over 4. Now, this is in this form, we have a complex number in the polar form. And also it is in the polar form, it is better to transfer into or to express it in the complex, in the algebraic form. In algebraic form, we can transform this one, we have that z0, this one is the same as the square root of 2, because we have a 2 power 2, then here power 4, it remains with this one. Then you have a cosine of this, cosine of pi over 4, it is the square root of 2 over 2. Then plus I, sine of pi over 4, which is the angle of 45, then it is equal to square root of 2 over 2. And this implies that our z0 will be equal to, here we multiply, you get 1, then plus I. This is the first any fruit of that complex number z. So here it seems that our first n fruit of this one, it is this, and you can proceed to z1 if this is for k equal to 1, and if k is equal to 1, you can apply the formula. The formula is the same, you plug in this formula, then after plugging in the formula, you get those n fruit of those complex numbers. In this is just an example. You find that z1 is equal to this one, and z2 is this one when you plug in that formula, and finally you get z3. For k is equal to 3, you get this one. Now this shows that our for z, which is equal to -4, its roots, its fourth roots are z0, which is equal to 1 plus I z1, which is equal to -1 plus I, and z2 -1 -I, and z3, which is equal to 1 -1 minus I. So the remaining, it is to represent those any fruit of this complex number z -4 in the eigenplane. In this case, we have our eigenplane where here we have imaginary part or imaginary axis, and here you have a real part. Now you know that to represent this one, here you can have I, 2I, 3I, 4I, 5I, 6I, 7I. You can remove those i's or not. Now you have -I, -2I, -3I, -3I, 4I, and so on and so forth. Here you have a 1, 2, 3, 4, 5, and so on and so forth. Here you have -1, -2, -3, -4, -5. Now, what we want is to represent those fourth root of these complex numbers. Z0, for example. If we are going to represent this is Z0, we represent this is Z0 in this eigenplane, and it is 1 for real part and 1 in imaginary part. In this case, we have that it is this one. We have a 1 on real part and 1 in imaginary part. Let's use the good scales so that it can be visible for all. Let's say this be 1, this will be -I, and this be 2I, this will be 3I, and here you have 2 and a 3. And here you have a -I, -2I, then 2, 1, -1, -2. Now, to represent this 1 and 1, you have a z0. It means our z0 would be here. And here it is our z0. And our z0, you know that is 1 plus I. It is in the first quadrant. Now, this z1, it is -1 and I. -1 is in this case -1 and I. It is there. Here. This one. This is our z1. And then you represent z2, -1, -1. It means it is -1, -I. It is in here. This is our z2. And z3, it is 1 and -1 here. And here it is our z3. So that's the case of representing those ones. And you know, you have to know that we have our modulus, and that modulus, it is from the origin to that point. And it is this one. For example, this is our first one, z1, and here I have a z0. So we can say that this one can form a shape. For example, you can join in this one, this and this and this one, and you get a shape. So it is also another case of representing those ones, and you can even form a shape of a one of quadratic. You can construct a square from this one. It is constructed as a square because n is equal to 4. And if n is equal to 4, we know that our cycle have 4 sides. If they have 4 sides, it can be made of those 4 points, and those 4 points you can join them to have this shape of a square. Now, that's the case. And also, we can even talk about what we call the sum cases. So this is just an example. You can have a different more and try to find those, they are corresponding any fruit of those complex number, and you present them in a plane. So let's have another case of a unity. So for the cases of any fruit of the unity if it is a unit, it means that z is equal to 1, and if z is equal to 1, in this case we know that our angle is equal to here, it will be equal to 0. And then if z is equal to this one, its modulus is equal to 1 and the angle is equal to 0. It is 0, why? Because it is in the first quadrant and you have only 1 in that direction of cosine. Cosine is equal to 1 and the sine is equal to 0, and this one is our argument. So you know that zk, the any fruit of this one, it will be 6 of 0 plus 2k pi over n. Now, this varies from n. For n equal to 2, we are going to have a z0 and z1. Here you have 2 points. And then for n equal to 3, here we have a z0, z1 and z2. That's another case. If you represent them, you have 3 points. And those 3 points can form what we call a triangle of 3 sides. And also we can have for n equal to 4. And if for this one we have a z0, z2, z1, z2, and z3. In this case, you have 4 sides and you have 4 points. And if we join those 4 points, you can have a square. And also, for example, if n equal to 5, if n equal to 5, you can have a z0, z1, z2, z3, z and z4. In this case, you can join those ones, and if you join them, you have a pentagon. So we represent a polygon. From n, if n is greater than 2, for example, 3, we start to form a shape. If there are 2, we have only 2 lines and 2 points. And 2 points cannot form a shape. But the 3 points, we can form a shape. And even the 4 and the 4 ones. So here you can have a triangle. Here for 4 you have a square. And if n is equal to 5, here you have a pentagon. And more and so forth. If we have n is equal to, for n is equal to 6, means you are going to have here you have a 5, and here for that one you have z0, z1, z2, z3, z4, and z5. And now you have a 6. If there are 6, in our case you know how to call them. From those, if the n is greater than 4, we are going to have a polygons. And those polygons, you know their names. So let's do one example from this one, then we represent those these polygons we are talking about, then we see how they are related to the upper concepts. So let's take an example. If z is equal to 1, it is a unit, you know. Its argument will be equal to 0, you know, 0 degree. And let's start from the case of where n is equal to 2. If the n is equal to 2, it means you are going to find n fruit. And this one will be zk will be equal to what? It is root n r, and in that case r is equal to 1. If r is equal to 1, there is no need of writing this one. It means you can use cosine of 0 plus 2k I. N is equal to 2 over 2 and plus I sine 0 plus 2k I over 2. Now, if we have this case, we can have k will be, if n is equal to 2, k is equal to 0 and 1. So z1, z0 will be equal to what? It will be equal to z. This is cosine of 0, k is equal to 0, it is cosine of 0 plus sine of 0. And you know that z, in this case, implies that z0 will be equal to what? Cosine of 0, you know it is 1, and cosine sine of 0 is equal to 0. And this shows that z0 is equal to 1. And also, this is our in algebraic form, and this is in polar form. So let's find z1. Z1 you place, you plug it there. It is the cosine of, this is a 0, then you add the k is equal to 1, you have 2. 2k, 2 pi over 2. 2 pi over 2 is equal to pi plus I sine of pi. And this case we have this one, and this implies that z1 will be equal to what? Cosine of pi. Cosine of pi is equal to second quadrant, and for one, this one it is be -1, and the cosine of pi, sine of pi will be equal to 0, and then it is this one. So to represent this in Argand plane, you know that we can use the one we have here. So after finding those any fruit of this complex number, it seems that now the two roots of of z which is equal to 1 r, our z0 which is equal to 1 and z1 which is equal to -1. So to represent this one, it is simple. You have to know that you have 1. 1 is this point, and this is our z0, and -1 is our z1, and then you can plug. This is our z1 and this is z0. That is all for this case of the unit 1. And then let's have, for example, another case where n is equal to 3. Then we proceed to n is equal to 4, n is equal to 5. You will do that in your exercise ways. So let's take an example when n is equal to 3. Then we proceed to the presentation or representing those n equal to plus 1. And if you remember that we are doing with this is unit 1, where z is equal to 1 and its modulus is equal to 0. It is the case over there. And if n is equal to 3, we are going to have a z0, z1 and z2. In this case, you have found that z0 is equal to 1. You can proceed in the process of finding the n fruit. It is not our concern. And even you can, if you have a child, we can help you. Then z1 is equal to this one, mostly because we need to represent them. We can have this case of representing this in this form, and also this is z2. And to represent that, we have a z0 is equal to 1, and 1 it is already represented. We can use the same diagram, there is no problem. Let's call this one z0 for this n equal to 3. And also we have a z1 is negative 0.5 and 0.9. For example, you can say that 0.5 is this side, this one, and the negative point, that one. Let's call this one. Let this be z1. And z3, it is negative 0.5 and negative 0.9i. In this case, you can say that it is, for example, you can have, if this is negative I, you can suppose that this is our point. And then finally, what you have to do is to draw those lines joining those concepts. Then the case will be, this is z0, z0 is already, there is no problem. It is this one, then you have a z1